if we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, but when we add the second slit, if the top of one wave meets the bottom of another wave, they cancel each other out. So now, there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. But we get a pattern like waves, not like little marbles. How? It doesn't make sense. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. The observer collapsed the wave function simply by observing.
However, the double hole experiment's mind-boggling conclusions don't end there. In recent years, technology has allowed scientists to perform a fascinating variation of the test. Its results call into question our perception of time itself.
This is like a high-tech version of the double hole experiment. Electrons are being fired toward a barrier with two holes in it. But the scientists can delay their decision about whether to observe the electrons until after they've passed through the holes, but before they hit the screen. It's as though I'm on a baseball field, and there's a baseball being pitched toward the barrier with the holes in it. But my eyes are closed, so it goes through, and it behaves like a wave, but then, at the last second before it hits the screen, I open my eyes and decide to observe it.
At that moment, the electrons, in essence, become particles, and seemingly always were particles from the time they left the electron gun.
So it's as though they went back in time to before they went through the holes and decided to go through one or the other, not through both as they would have had they been behaving like waves. That's really crazy.
That's the enigma. That our choice of what experiment to do determines the prior state of the electron. Somehow or other, we've had an influence on it which appears to travel backwards in time.
The experiment begins in the top left corner, with the laser firing two entangled photons either through slit A or slit B. Now it is truly random which slit it will fire through. we cannot know which slit the laser fires through until they pass through and are detected on the other side. Now the first prism splits the entangled photon.
This is how it works. When two subatomic particles interact, they can become entangled. That means their spin, position, or other properties become linked through a process unknown to modern science.
If you then make a measurement of one of the particles, then that instantaneously determines what the behavior of the other particle should be. And when the experiment is done, it's found that indeed the other particle's quantum state is exactly determined once you've made a measurement of the partner particle's quantum state.
Now the first prism splits the entangled photons and sends them in different directions. The top one goes to detector 0. Now if the photons only hit D0, we don't know the path information, since when the photon arrives, it could have either come from path A or path B. So because we don't know the path information, it should produce an interference pattern if it only came here. So because of the lack of knowledge we would have about the system, the particle would act in a way as if it goes through both, becoming the wave of possibilities it could have been. But the other entangled photon goes the other way, and because it is entangled, it will affect the result of its twin that went to D0. Now the other photon from either A or B goes through the prism and hits either BSA or BSB. At both of these, there is a 50-50 chance it will either pass through or bounce off and go to either D4 or D3. Now if the photon hits either one of these detectors, notice what happens. We obtain which path information, because the only way the photon could hit D3 is if it came out of B, and the only way it could hit D4 is if it came out of A. So if a photon hits D3 or D4, we will know the path information it took, and we will get a clump pattern. Now if the photon randomly passes through BSA or BSB, it will either bounce off here or here, and it has a 50-50 chance of passing through BSC or bouncing off of it. So if the photon passes through BSA or BSB, we lose the path information, because if it hits D1 or D2, it could either have come from A or B. We can't ever trace the path information back to A or B. So when they hit D1 or D2, we should get an interference pattern. Now here is one of the important implications of this experiment about what is causing collapse. If a photon makes it to D1 or D2, they always display an interference pattern. Yet every time a photon hits D3 or D4, a clump pattern is formed. But the only difference between these two is what we, the conscious observer, knows about the system. Our knowledge of the system causes different results in how the photon will act. See, what causes collapse is knowledge, and knowledge requires a knower. Sir Rudolph Peirce said, "The moment at which you can throw away one possibility and keep only the other is when you finally become conscious of the fact that the experiment has given one result." You see, the quantum mechanical descriptions is in terms of knowledge, and knowledge requires somebody who knows. Now the other implication is even more mind-boggling, because the photon knew beforehand where it would end up. How do we know this? Because of how its twin acts at D0. The twin photon registers at D0 before its entangled twin ends up at a detector, and whatever registers at D0 always correlates to wherever its twin ends up. So if the twin hits D3 or D4, D0 always registers a clump pattern to correlate, and always an interference pattern if its twin lands at D1 or D2. John Wheeler said, "It begins to look as if we ourselves, by a last-minute decision, have an influence on what a photon will do when it has already accomplished most of its doing. We have to say that we ourselves have an undeniable part in shaping what we have always called the past. The past is not really the past until it has been registered. Or put it another way, the past has no meaning or existence unless it exists as a record in the present." Asher Perez, who developed the original thought experiment, says, "Curious paradoxes appear. Quantum effects mimic not only instantaneous actions at a distance, but also, as seen here, influence of future actions on past events, even after these events have been irrevocably recorded."
When detector 2 senses a photon, detector 1, which senses its entangled photon, shows that it's a particle, not a wave, because we see a double-line particle pattern. The same thing happens when detector 3 senses a photon. Detector 1 shows its entangled twin as a particle. However, when detector 4 senses a photon, detector 1 senses a wave pattern, not a double-line particle pattern, because its which path information is not known. So far, nothing is surprising here, right? But when the detector cannot ascertain which slit the photon came from, that is, when the which way information is erased, the photon acts like a wave. But I'm being a little cheeky here because I left out a tiny but crucial detail that makes these results shocking. And that detail is that the path to detector 1 is much shorter than the paths to detectors 2, 3, and 4. So the photon is always detected at detector 1 before it is detected at any of the other detectors. So this is the delayed choice aspect of this experiment. An interference pattern forms on detector 1 even if the which path information pertinent to the photons that form it are only erased until much later in time at detector 4. And a double line pattern forms at detector 1 even before its which path information is ascertained at detectors 2 or 3. This shows us that somehow the photon at detector 1 knows ahead of time which detector its entangled pair will end up at in the future. So it seems to show that the future state of the photon at detectors 2, 3, and 4 affect the past state of its entangled pair at detector 1. And these results are absolutely consistent and have been demonstrated in multiple experiments over and over again. How is this possible? What is absolutely clear in these experiments is that the measurement of a particle in the present can influence the properties of that particle in the past. In other words, a decision made in the present can influence something in the past. The effect seems to precede the cause. But maybe our sense of time flowing in one direction is not something that entangled systems are constrained by. The entangled particles seem to be immune to the direction of time or are somehow connected in time even when they're not connected in space. There can be no communication between the future and the past. This would violate all kinds of laws in physics, like conservation of information, conservation of energy, thermodynamic principles like entropy. The past cannot be changed. The past is fixed. Maybe the past can be changed. You can't change the past. Maybe the past can be changed. You can never change the past. How can you change the past? You can't change. Maybe the past can be changed? To be perfectly honest, I don't have an answer. No one has a good answer. If you have an answer, let me know because there's a Nobel Prize waiting for you.